Hi there, my name is Lori Shelton Penizak, and I'm a geologist here at Spectral Evolution. And today we're going to be talking about using a field spectrometer to identify contaminants in soil. So just a little bit about our company and who we are. Spectral Evolution was incorporated in June of 2004. We operate out of Haverhill, Massachusetts, and we are a full-line supplier of UV-VIS and NIR spectrometers for field portable mineral identification, core logging, remote sensing, and general photonics applications. The application that I focused on for this workshop is contamination of soils. Contamination of soil due to leaks, spills, and seepage is a worldwide problem, usually diagnosed by costly and time-consuming methods like wet chemistry. A faster solution to identify contaminants in soil is to use a UV-VIS-NIR field spectrometer. It's a good alternative because in about 3 seconds, your spectral data appears and you don't have to prepare or destroy your sample. Throughout this presentation, we will be focusing on hydrocarbon contaminants like diesel, gasoline, and oil. So let's talk about the instrument that was used in this study, which is our OR Expert. The OR Expert is an ultra-high resolution spectrometer that is full range, which covers 350 nanometers to 2500 nanometers. This portable spectrometer is actually the highest spectral resolution on the market, with a 1.5 nanometer resolution in the ultraviolet, 3 nanometer in the visible, and 3.8 nanometers in the near infrared. This resolution gives you about double the resolution you'd get with a standard resolution instrument, meaning better quality data for you. So again, the contaminants that were used in this study are diesel, gasoline, and engine oil. So here we are looking at the spectral reflectance of our contaminants. Diesel being the red, gasoline in green, and engine oil in blue. We are looking at full range, 350 to 2500 nanometers. There are 4 regions of hydrocarbons: the 1120 to 1240 nanometer region, the 1350 to 1450 nanometer region, 1700 to 1770 nanometer region, and the 2290 to 2360 nanometer region. The 2 main regions that are generally used are the triplet feature at 1700 to 1770 nanometers and the triplet feature at 2290 to 2360 nanometer region. This is mainly due to heavier hydrocarbons occurring in those regions versus the lighter hydrocarbons occurring at the 1120 to 1240 and 1350 to 1450 region. We can actually distinguish which hydrocarbons based on the shape and spectral shift of the feature. So let's talk about what exactly is causing those features. So again, the most important hydrocarbon features occur with the triplet between 1700 and 1770 nanometers, which can be attributed to the first order overtones and combinations of the various CH stretching fundamentals, and also the 2290 to 2360 region, which is affected and attributed by numerous overlapping combination and overtone bands from the 1700 to 1770 nanometer region. Although hydrocarbon features are present at the 1120 to 1240 and 1350 to 1450 nanometer region, they should be discretely used because of the closest to absorption range of water resources absorption range at 1400 nanometers, also due to the light hydrocarbon tendencies of the 1120 to 1240 nanometer region. A lot of times this region is very minute. While still visible, the features are very small in soil samples, which I will point out later. Therefore, the spectrum of soil samples that were used in this study were examined in terms of presence of hydrocarbons only in absorption ranges of 1700 nanometers to 1770 nanometers and the 2290 to 2360 nanometer region. The initial soil samples that were collected were not contaminated. I actually added in different percentages of contaminant to each sample. So the soil samples collected all came from different locations, and shout out to the University of New Hampshire for going out and collecting these samples for me. So samples ML came from the McLennan Reserve and are classified as a clay loam with a dominant mineral being montmorillonite. The BR samples are from the Black Rock Consortium, classified as sandy loam with dominant being illite, and the PF samples come from the Pittsfield State Forest and are classified as silty clay loam with illite. So if we look at the spectral reflectance of the soils before they were contaminated, the 1400, 1900, and 2200 nanometer regions are assigned to the structural and adsorbed water in the clays and to cation OH vibrational bands. The wavelength position of the 1900 nanometer band at 1920 does not coincide with that expected of free water. The broadness of this band in the 1400 nanometer band is consistent with the presence of water in a variety of sites or with structurally disordered clays. The materials and methods for contaminating these soils, I had 54 total samples, 18 from each location. Once these were dried out in the oven, I had about 3.3 grams of each sample. So each location sample had a concentration of 0.012 ounces with all three contaminants, 0.032 ounces with all three contaminants, and 0.052 ounces with all three contaminants. Now the 0.012 ounce is going to be the least saturated and the 0.052 being the most saturated. Now this was done by putting each soil sample into a sample tray, then adding the measured out contaminant. It was then compacted down. The benchtop probe light source was used with the ORExpert to acquire these sample spectra. All right, so let's take a look at the results. First, we are viewing the diesel contaminated soil from all three locations. The first thing I'd like to point out here is that there is a trend among all of the contaminants that as you increase the amount of contaminant, so going from 0.012 ounces to 0.052 ounces, the reflectance percentage of the sample does decrease, and this is directly related to the increase of the contaminant. The second thing I want to point out is that at 1200 nanometer region, there is a very small light hydrocarbon feature that is more visible in the saturated 0.052 ounce contaminant soil samples, although still a very weak absorption depth. The feature at 1400 nanometers, although light hydrocarbons do absorb here, is hardly considered as an absorption range of the hydrocarbons in soil in particular due to the overlapping with range of water absorption. So throughout all of these samples, we will classify that region with the OH from the clay rather than a true hydrocarbon feature. At 1700 to 1770 nanometers, we have a triplet hydrocarbon feature here. So note how the depth increases as contaminant increases. The most prominent absorption band attributable to the various forms of water is present at 1900 nanometers and is most intense in the most water to clay rich samples. So this wavelength region is useful for clay water discrimination because unlike the 2290 to 2360 nanometer region, it is not significantly overlapped by hydrocarbon absorption. The broadness and complex shape of the 1900 nanometer band is consistent with the presence of water in a number of sites in the clay, structurally disordered clays, or more than one species of clay. Clay lattice OH bands, specifically ALOH, is present at 2200 nanometers, correlating to the clay in the soil samples. And finally, the hydrocarbon feature at 2290 to 2360 nanometer region. So you can clearly see the hydrocarbon features from the diesel within our soil spectra. So these samples were contaminated with gasoline, and they actually show a shape and broadness of the hydrocarbon feature that is different than what we had with a diesel. So the distinction here will make it easier to identify a gasoline contaminant versus a diesel contaminant. So these are the spectra from the soil contaminated with engine oil. The hydrocarbon feature here does look very similar to that of the diesel. However, we do experience a spectral shift to the right for the engine oil hydrocarbon. So one could also distinguish hydrocarbons based on their spectral shifts. So to do a quick and easy identification of contaminants in soil, our EasyID identification software is a great tool that uses built-in or self-made libraries to instantly identify key features. So in our case study, we can use the shape and spectral shift of hydrocarbons to identify which type of contaminant is present in unknown samples by using hydrocarbon presets. So in conclusion, using a field-portable UV-VIS-NIR spectrometer assists in identifying hydrocarbons in contaminated soils without sample prep or destruction. The 1700 nanometer region and 2290 nanometer region are dominant heavy hydrocarbon regions and can be seen in different types of soil. EasyID is a great tool to identify these different hydrocarbon contaminants. So if you would like more information on our EasyID software or the instrument that was used in this study, make sure you contact myself or info@spectralevolution.com, and also follow us on LinkedIn and YouTube. Thank you.